In the late 1990s, Intel and Hewlett-Packard set out to redesign the brain of the computer from first principles. They poured billions of dollars, thousands of engineer years, and the future of their high-end server businesses into a single idea: that the way we build processors was fundamentally wrong. The result was called Itanium. On paper, Itanium was supposed to replace not just Intel's aging x86 line, but most of the world's powerful server CPUs. It was meant to usher in a clean, 64-bit future, free of old architectural baggage. Industry analysts predicted that by the mid-2000s, almost every big server would be running Itanium. That never happened. Instead, Itanium became one of the most consequential missteps in processor history. A chip family that shipped for nearly 2 decades, powered some very serious machines, and yet is mostly remembered as a cautionary tale. This is the story of why Intel and HP were convinced they had to gamble on Itanium, what made its technology genuinely different from the processors most of us use today, and how that very difference became both its greatest promise and its downfall. To understand why Itanium existed, we have to go back to the mid-1990s. By then, Intel's x86 architecture, born in the late 1970s, was everywhere. Desktops, low-end servers, workstations, but the design was showing its age. It was a 32-bit instruction set, layered with decades of quirks and special cases. Implementations had become extremely complex just to keep up with performance demands. At the same time, the industry knew 64-bit computing was coming. High-end servers and scientific machines were already using 64-bit RISC chips from companies like DEC, Sun, and IBM. These processors could address vastly more memory and handle large integer and floating-point workloads more cleanly than x86. Intel faced a dilemma. Extending x86 to 64 bits looked ugly and risky. The instruction set was tangled, and any change had to preserve compatibility with a massive existing software base. On top of that, Intel's relationship with AMD, its main x86 competitor, was complicated. Licensing deals and lawsuits over the years had given AMD a foothold in producing x86-compatible chips. Intel was not eager to anchor its future entirely to an instruction set it didn't fully control. Hewlett-Packard, meanwhile, had its own problem. HP's high-end servers used a line of 64-bit RISC processors called PA RISC. They were capable, but HP saw limits in the roadmap. Pushing PA RISC further was going to be expensive, and HP didn't have the volume or ecosystem that Intel did. So, rather than compete, Intel and HP chose to join forces. In 1994, they announced a joint project: a next-generation, 64-bit architecture that would, in theory, replace both HP's PA RISC and eventually Intel's high-end x86 servers. HP would contribute architecture ideas. Intel would bring manufacturing muscle and market reach. Internally, this new design was seen as a clean break, a way out of decades of technical debt and licensing entanglements. It would not be x86-64, it would be something entirely new. The new architecture needed a technical foundation that justified such a risky break with the past. The answer they settled on was called EPIC, explicitly parallel instruction computing. To grasp EPIC, it helps to contrast it with what most high-performance CPUs of the 1990s were doing. Those processors were called out-of-order superscalar designs. In simple terms, the program you write is a long list of instructions. Do this, then that, then the next thing. But modern chips don't like going step by step. They want to do as many operations at once as possible. In an out-of-order superscalar CPU, hardware inside the chip analyzes this stream of instructions on the fly. It looks ahead, reorders operations that don't depend on each other, speculates past branches, and keeps multiple execution units busy in parallel. This requires enormous complexity: large reorder buffers, issue queues, dependency checkers, and elaborate branch prediction. EPIC flipped this around. Instead of the chip figuring out what can run in parallel at the last moment, the compiler, the software tool that turns high-level code into machine instructions, would do that work ahead of time. This approach traces back to an older idea called VLOV, or Very Long Instruction Word. In a classic VLE machine, a single, wide instruction word encodes multiple operations that are guaranteed to be safe to run together. The hardware doesn't need to guess, it just executes what the compiler has already grouped. EPIC extended this philosophy. The core bet was, if the compiler can analyze the program statically, with a global view of its control flow and data dependencies, It can schedule instructions more intelligently than hardware reacting cycle by cycle. That would allow the chip itself to be simpler, less out-of-order machinery, more room for raw execution units and registers, and in theory, higher performance and lower power for a given level of parallelism. So the Itanium architecture was built around making that parallelism explicit. Instructions were packaged in ways that told the hardware which operations could safely run side by side and which had to wait. The promise was a future where compilers, not silicon, did the hard work of extracting performance. To see how this worked in practice, we have to look at the structure of Itanium's instructions. Instead of issuing one instruction at a time, Itanium used 128-bit bundles. Each bundle contained 3 individual instructions, plus a few extra bits of control information, called template bits. Those template bits told the processor how the instructions in the bundle and across adjacent bundles could be executed. The key concept was the instruction group. An instruction group was a sequence of operations that the compiler promised had no conflicts and could all be issued in parallel. The template bits encoded where one instruction group ended and the next began. Inside a group, the hardware was free to execute the operations simultaneously, up to the limits of the functional units. Between groups, the hardware had to respect order. This is where the explicit in EPIC shows up. The parallelism is baked into the code itself. The compiler schedules instructions into these groups, taking into account dependencies, resource usage, and expected latencies. In theory, this means the chip doesn't need heavyweight logic to figure out which instructions are independent. It just sees, here is a group, these can run together, here is a boundary, now we must preserve order. Itanium implementations still had some dynamic behavior, like handling cache misses or unpredictable events. But the overall scheduling philosophy was fundamentally different from a classic out-of-order core that reorders almost everything internally. For developers, this meant that the quality of the compiler scheduling decisions had a direct and visible impact on how well the machine ran. The binary itself effectively contained a pre-computed execution plan. Another distinctive feature of Itanium was predication, a mechanism designed to reduce the performance cost of branches. In a normal program, you constantly make decisions. If this condition is true, do one thing, otherwise do something else. In hardware, these turn into branch instructions. Branches are problematic because the processor has to guess which way the code will go before it knows the outcome. If it guesses wrong, it has to throw away work it already did, wasting time. Predication offers a different approach. Instead of branching, many instructions in Itanium could be guarded by predicate registers, special 1-bit flags. An instruction might say, in effect, add these numbers, but only actually write the result if predicate P is true. If P is false, the instruction executes but its result is discarded. This allows the compiler to convert small conditional blocks into straight-line code. Both the if and the else paths are laid out as a sequence of predicated instructions. The processor doesn't need to branch, it just runs through the instructions, with predicates determining which ones take effect. On an EPIC machine, this meshes well with static scheduling. By reducing the number of hard branches, predication gives the compiler more room to form long instruction groups that span what would otherwise be split into separate paths. Of course, predication isn't free. You may end up executing instructions whose results are thrown away, which costs power and potential performance. The compiler has to choose carefully when predication is better than a branch. But as a tool, it was central to Itanium's strategy. Transform control flow into something the static scheduler can reason about more easily, and in the process, keep the execution units fed without the constant disruption of mispredicted branches. Memory access is another major source of unpredictability in modern CPUs. The processor runs much faster than main memory, so it relies on caches, small, fast memories close to the core. When data is already in cache, loads are quick. When it's not, they can stall the processor for many cycles. An out-of-order core hides some of this by juggling other independent instructions while a slow load is in progress. But on a statically scheduled EPIC machine, much of that juggling has to be planned ahead of time by the compiler. To help, Itanium introduced aggressive support for speculative loading. Compilers could insert load instructions earlier than strictly necessary, before it was certain that the data would be needed or that the address was even valid in the current control path. The architecture provided special forms of loads and associated check instructions that allowed the hardware to detect if something went wrong, like a cache miss that turned into a page fault, and recover in a defined way. The idea was that the compiler could pull loads up, schedule useful computation in the gap while the memory system did its work, and then later insert checks to ensure that the speculation hadn't triggered an exception that needed to be handled. Combined with hints about expected memory behavior, this speculative machinery was supposed to let the static scheduler approximate what an out-of-order core does dynamically, overlap long latency memory operations with other useful work. But this also made the compiler's job significantly more complex. It now had to reason not only about data dependencies, but about when and where it was safe to speculate and how to structure recovery paths. As we'll see, exploiting this potential in real-world, mixed workloads turned out to be far harder than early advocates hoped. A third pillar of Itanium's design was an unusually rich register architecture. Registers are the tiny storage locations inside the CPU where it keeps values it's actively working on. Accessing registers is much faster than going to memory, so having more of them lets the processor keep more intermediate results close at hand. Itanium provided a very large set of general registers, as well as dedicated register files for floating point values, predicate bits, and control information. It also featured a sophisticated mechanism called rotating registers, particularly useful for loops. In a typical loop, say, processing elements in an array, you often have the same pattern of operations repeated with different data. Rotating registers let the compiler treat groups of physical registers as a circular buffer. On each iteration, the mapping from logical to physical registers shifts. This makes software pipelining of loops much easier. You can have different iterations of the loop in different stages of completion, all overlapping in time, without their values colliding in the register file. Alongside this, Itanium used a form of register stacking for procedure calls. Instead of constantly saving and restoring registers to memory on every function call, the architecture treated part of the register file as a stack that could slide up and down, giving each function its own window onto the larger pool. All of this served the same goal: expose as much instruction-level parallelism as possible, and give the compiler enough architectural headroom to keep the machine busy. With abundant registers, predication, and explicit instruction grouping, the architecture invited compilers to build long, carefully orchestrated sequences of operations that would keep many execution units working in parallel. The catch was that this orchestration had to be right. If the compiler misjudged memory latencies, branch behavior, or resource usage, there was little the hardware could do on its own to save performance. That brings us to what many people consider Itanium's central Achilles heel: the compiler problem. The EPIC philosophy assumes that the compiler can see far enough ahead and model the machine well enough to schedule instructions nearly as effectively as a sophisticated out-of-order core could do at runtime. In simple, regular workloads, tight numeric loops with predictable memory access, this is often feasible. Compilers had been doing advanced loop optimizations and instruction scheduling for years on traditional architectures, but large, real-world server applications are messy. They have pointer-heavy data structures, unpredictable branches based on user input or network traffic, and memory accesses whose latency swings wildly depending on cache state and system load. Static scheduling around such unpredictable memory behavior is incredibly hard. The compiler has to guess how long loads will take, where to insert speculative operations, and how deeply to pipeline loops without causing resource conflicts. On top of that, Itanium's full feature set, predication, rotating registers, software pipelining, speculative loads with checks, created an enormous space of possible code shapes. Finding the best one is a complex optimization problem. Toolchains from HP, Intel, and third parties improved over time, but they were racing against both the complexity of the architecture and the rapid evolution of software. Many developers found that unless their code was compiled with very specific flags and often tuned by experts, Itanium systems did not live up to the performance implied by their raw hardware resources. There is some disagreement among engineers and historians about the balance of blame here. Some argue that compiler technology eventually caught up enough, but by then the market had moved on. Others say the architecture itself demanded an unrealistic level of foresight from compilers, and that no amount of tool work could fully compensate. What's clear is that the EPIC bet tied the architecture's success tightly to advances in compiler analysis and optimization that were not fully mature when the first chips arrived. The first Itanium chip, codenamed Merced, became a case study in the difficulty of turning ambitious architectures into working silicon. Intel and HP originally announced their joint project in 1994, with plans that suggested commercial systems before the end of the decade. Hype built steadily through the mid-90s. Trade press articles described Itanium as the inevitable successor to both x86 servers and many proprietary RISC systems. But Merced slipped, again and again. Design complexity, verification challenges, and the need to coordinate hardware with evolving compilers all contributed to delays. Public statements and leaked roadmaps from that era paint a picture of schedules pushed back by a year, then another year. When Merced finally shipped in 2001, it landed with a thud. On well-tuned floating-point benchmarks, it could look respectable. But on many real workloads, especially general-purpose integer and business applications, performance was disappointing compared to high-end x86 and RISC competitors of the time. Some observers pointed to immature compilers, others highlighted micro-architectural choices in Merced itself, like limited cache sizes and conservative clock speeds, as reasons it failed to showcase the potential of the EPYC design. Whatever the exact mix of causes, and accounts differ on the internal postmortems, the gap between years of marketing promises and the delivered product eroded confidence. Customers who had been told to plan their long-term roadmaps around Itanium began to hedge, keeping investments in existing x86, PA RISC, or other RISC systems. Merced was widely seen as a first pancake version, a necessary step to get the architecture out the door, but not the chip that would redeem the project's ambitions. Intel's second-generation Itanium, codenamed McKinley, and launched in 2002, addressed many of Merced's shortcomings. It had higher clock speeds, a redesigned core, and a much stronger memory subsystem. Later iterations, like Madison and Montecito, added larger caches, dual-core configurations, and various micro-architectural tweaks. Over time, these improvements, combined with maturing compilers, did yield solid performance in certain niches. High-end HP servers running HP-UX, and later some Linux and Windows Server deployments, used Itanium systems for large databases and mission-critical enterprise workloads. In these environments, Itanium's large caches, robust error-checking features, and focus on instruction-level parallelism could shine on carefully tuned code. HP in particular invested heavily in software optimization, tooling, and customer support around Itanium, positioning it as the successor to both PA RISC and some of its earlier proprietary platforms. However, this success was narrow. Itanium struggled to win broad adoption beyond a handful of vendors and specialized markets. Many software vendors were reluctant to port or deeply optimize for a platform whose long-term future was already viewed with some skepticism. Still, it would be a mistake to say Itanium never worked well anywhere. For a period in the 2000s, there were real systems in real data centers, relying on Itanium for critical workloads, and getting acceptable, sometimes strong, performance. The architecture's technical merits mattered there. They just never translated into the mainstream dominance originally envisioned. While Intel and HP were trying to build Itanium up from the high end, a quiet development on the x86 side would ultimately undercut the architecture's central rationale. In the early 2000s, AMD introduced a 64-bit extension to the x86 instruction set, initially called AMD 64 and later widely known as x86 64. Instead of discarding the old architecture, AMD bolted 64-bit capabilities onto it in a way that preserved compatibility with existing 32-bit software. This was a more conservative, less elegant solution than a clean-sheet design like Itanium, but it was exactly what the market needed. Server buyers could move to 64-bit address spaces and larger memories without abandoning their software ecosystems. Operating systems quickly added x86 64 support, and compilers learned to target it effectively. Intel initially resisted AMD's approach, preferring to keep pushing Itanium as its 64-bit path. But customer demand for a compatible 64-bit x86 was overwhelming. Intel eventually adopted essentially the same extension under its own name, Intel 64. At the same time, commodity x86 servers were getting more capable. Multi-socket configurations, growing core counts, and maturing operating systems made large x86 64 clusters increasingly attractive. The performance gap between high-end proprietary architectures and mass-market x86 narrowed. For Itanium, this was devastating. One of its original justifications had been, we need a new 64-bit architecture to move beyond the limits of x86. Once x86-64 existed and worked well enough, that argument largely evaporated for mainstream servers. Itanium was left to compete as a specialized, expensive platform in a world that was standardizing on a cheaper, more compatible alternative. Its technical distinctiveness no longer aligned with the direction of the broader market. As the 2000s wore on, the signs of Itanium's decline became harder to ignore. Fewer hardware vendors built new Itanium systems, some early partners quietly stepped back, choosing instead to double down on x86-64 or their own risk lines. HP remained the strongest backer, essentially tying its high-end Integrity server line to Itanium's fate. Software support began to fray. The most public flashpoint came in 2011, when Oracle announced it would discontinue developing new versions of its database and other software for Itanium. HP argued that Oracle was trying to sabotage a competitor's platform. Oracle countered that Intel's roadmap made Itanium a dead end. The dispute escalated into a high-profile lawsuit, with courts eventually ordering Oracle to continue supporting Itanium for a time. Behind the headlines, other vendors and open-source projects quietly scaled back or dropped support as well. Maintaining a high-quality port for a shrinking user base is expensive, and engineering resources tend to follow the largest markets. Intel, for its part, kept releasing updated Itanium generations through the 2010s, though on a slower cadence and with less fanfare. The chips grew more capable in absolute terms, but their relevance shrank as x86-64 and later, alternative architectures like ARM made gains in servers. By the mid-2010s, Itanium shipments were largely confined to a dwindling number of high-end HP systems, often sold to existing customers with long upgrade cycles. New design wins were rare. Intel announced the final Itanium generation, codenamed Kitson, with a muted roadmap, and eventually confirmed the end of the line. The last Itanium processors shipped in the late 2010s, and HP, by then Hewlett-Packard Enterprise, set timelines to end support for Itanium-based systems in the years following. What had once been pitched as the universal future of 64-bit computing exited the stage as a niche legacy platform. Looking back, Itanium is often summarized as a failure. In commercial and strategic terms, for Intel and HP's original goals, that's hard to dispute. The architecture never became the dominant 64-bit platform it was intended to be, and the investment it consumed helped reshape the fortunes of both companies' server businesses. But its story is more nuanced than a simple cautionary slogan. Some of Itanium's ideas, extensive predication, sophisticated register management, aggressive speculation support, found echoes in later designs, even if not copied directly. Modern out-of-order cores, GPUs, and specialized accelerators all grapple with the same basic question: how do you extract parallelism from code that wasn't written with parallel hardware in mind? In that sense, Itanium was an ambitious exploration of one extreme of the design space: push as much of the decision-making as possible into the compiler and the static instruction set, and simplify what the hardware has to do on the fly. The broader lesson, many architects would argue, is about balance and timing. Betting an entire general-purpose architecture on compiler technology outpacing hardware mechanisms turned out to be risky. Compilers did improve, but not always in the ways or on the schedule that Epic's success required. Meanwhile, traditional out-of-order designs kept getting better, absorbing some of the same concepts while preserving compatibility. There are still domains, like embedded DSPs and some accelerators, where VIW-like approaches make sense. In tightly controlled workloads with stable code and predictable behavior, static scheduling can work very well. Itanium's fate suggests that making that model the backbone of a universal server architecture is much harder. In the end, the cost and consequence of Itanium lie not just in money spent, but in the opportunity paths it closed off or delayed. Intel's eventual embrace of x86-64, HP's pivoting server strategy, and the broader industry's consolidation around a few dominant architectures were all shaped, in part, by the arc of this project. The story that began as a bold attempt to escape the gravity of legacy design ended up reinforcing a different reality. In computing, history is stubborn. Clean breaks are rare, and when you bet on rewriting the rules of how processors work, the code that really matters may not be running on the chip at all, but in the compilers that feed it.